Hello students, we are going to solve this JEE Mains 2025 question now. It's a question on rotational motion. It says that when a solid sphere and a hollow sphere roll down an inclined plane, which of these two objects will take a lesser time, or will they take equal times? That is what we have to find out. So we have to basically compare T1 and T2. So T1 is the time taken by the solid sphere. So T1 corresponds to solid sphere, and the time T2 corresponds to hollow sphere. And what is the expression for time? How do we get that? So from 1D motion, we know that distance or displacement is given by ut plus half at square. In this case, distance would be this. Let's call it s. And initial velocity is 0. Half acceleration is what we need to know. So if acceleration for solid sphere is more, it would take lesser time. If acceleration for solid sphere is less than that of hollow sphere, it would take more time. So our main goal is to find out this acceleration, t square. This is s. So 2s by a gives us t. We see that. Okay. Since the distance is the same, if somehow we can find out the acceleration, we would know how times compare to each other. For such cases, if you remember, acceleration was given by g sine theta by 1 plus the moment of inertia upon mr square. Now we'll use this to compare the two. But we have one question, how do we get this? So I'll revise that also for you, okay? Acceleration for the solid sphere is going to be g sine theta, where theta is this angle, and g is the acceleration due to gravity. 1 plus the moment of inertia for a solid sphere. If you remember, it's 2 by 5 mr square. So 2 by 5 mr square divided by mr square, you'll just get 2 by 5. So we are going to get 5g sine theta by 7. Similarly, if we do that for a hollow sphere, acceleration of a hollow sphere, we're going to get, instead of moment of inertia 2 by 5 mr square, we're going to put 2 by 3 mr square. So g sine theta upon 1 plus 2 by 3. This is what we get, and we'll get 3g sine theta upon 5. So this is the acceleration for the hollow sphere. This is the acceleration for the solid sphere. Now let's compare the time, because that is what we had to compare, right? And we know that time is given by root 2s by a. So we got acceleration for solid sphere as 5 by 7 g sine theta. Acceleration for hollow sphere, we got g sine theta. And we also know that time was given by 2s upon a. So T1 will get 2s upon acceleration of solid sphere. That would be T1. And T2 would be 2s upon acceleration of hollow sphere. And we have to find their ratio. Is the ratio 1? If the ratio is 1, then we can say option 2 is the correct option. If T1 comes out to be bigger than T2, accordingly, we can say option 4 is correct, and so on. So let's figure this out. T1 by T2. It's basically acceleration of hollow sphere upon acceleration of solid sphere under root. Because 2s is same, they'll cancel out. G sine theta is same in both these quantities, so we'll just use the numbers. This one and this one should be sufficient for us. So this comes in the numerator, 3 by 5, and then 5 by 7. This is 3 by 5 into 7 by 5, that is 21 by 25. So T1 is to T2 has this ratio. Of course, we can see that the denominator is bigger. So we can say that T2 is bigger than T1. T2 is bigger than T1. This is not correct. This is not correct. T2 is bigger than T1. This is also not correct. Option 1 is correct. So now our goal is to find out how did we get the acceleration of an object rolling down an incline to be equal to this thing, g sine theta upon 1 plus moment of inertia upon mr square, where g is acceleration due to gravity, theta is the inclination of this inclined plane, it's this theta, I is the moment of inertia about the center of mass. By the way, this is moment of inertia about center of mass, okay, not about the axis of rotation here. So if I'm taking the hollow sphere, I'll have to take moment of inertia for a hollow sphere. If I'm taking a cylinder, I'll have to take moment of inertia for a cylinder, and so on. Okay. M is the mass of this object. R is the radius of this object. Okay. A is, of course, the acceleration of center of mass that we are finding out. Because this object is rolling, so different points on this object will have a different acceleration, net acceleration, but we are concerned about the acceleration of center of mass alone. Okay, how did we get this formula? So we balanced forces. We balanced forces and we balanced torques. That's how we got two equations, and then when we solve those two equations, we get this as the acceleration. So now, let's first draw the free body diagram of this. What are the forces acting on this object? We have this sphere. So normal reaction would be acting this way. Frictional force would be acting this way. And mind you that this is pure rolling. This is frictional force. What other force would be acting? mg, which is the weight of this body. So these are the only three forces which are acting on this body. The normal reaction here, the frictional force here, and the weight of this body. So now, let's write the equation for translational equilibrium, which is balancing forces. Summation of all the forces is going to be equal to mass of this object into the acceleration of the center of mass of this object. So this is what we are going to do now. If you do that, we are going to get mg acting this way. If this is theta, this will be theta. This is mg cos theta. This would be mg sine theta. So we get mg sine theta minus this frictional force. Frictional force is equal to what? Mass of this object into acceleration of center of mass. This is our first equation. Then we'll write the equation for rotational motion as well. So rotational equilibrium. Which says summation of all the torques is 0 if the body is in equilibrium, but this one is not in equilibrium. So we'll say summation of all the torques is responsible for its angular acceleration, which is given by torque is equal to I alpha. Now, what is the torque about the center of mass? What are the forces that are contributing to torque about the center of mass? It's only one force, which is the frictional force, because both normal and the weight, they're passing through the center of mass. So the distance of the point of application of these forces from the center of mass is actually 0. So no torque will be contributed by the normal reaction force, and no torque will be contributed by this mg, weight. So only force contributing to this torque would be this friction. And what would be the value of it? Friction into the distance from the center of mass. So frictional force into R. This is the total torque acting on it. And we know that total torque is given by I into alpha. But what is alpha in terms of acceleration of center of mass? It's acceleration of center of mass upon the radius. So this is another equation we get, which is Fr squared is equal to I acceleration of center of mass. Now these are the two equations. If you solve this, and if you try to find out this, you will get this thing. So that's how we get to this formula. So what we've done, a quick summary of what we've done in this problem. We started to figure out whether a solid sphere rolls down an incline quicker or a hollow sphere rolls down an incline quicker. So acceleration due to center of mass depends on the moment of inertia. And that's how we figured out T1 and T2, and then finally found out the relation between the two. Please stay tuned for similar solutions. Thank you so much for joining.